Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at sorting algorithms, and in particular we will be looking at counting sort and Radix sort. So, what is the problem here? We have been given a set of integers and we want to sort the set of integers in an ascending order. For example, if we have this set S, which is 1, 4, 2, 10, 5, 8, 15, 13, 7, 8 and 1, we want to get some output like this 1, 1, 2, 4, 5, 7, 8, 8, 10, 13 and 15. So, till now we have looked at quite a number of sorting algorithms, and in all of them we have told that these integers are just an example. We can use any set of elements for which there is a total ordering. That means, we can compare between two elements. So, in fact, there are a lot of algorithms in this field. In general, we have still now looked at something called a comparison based algorithms, where the algorithms are based on comparing two items. So, we do not use any structure of the elements, we just ask is A bigger than B or B bigger than A, and then we keep on going accordingly. And therefore, it works for all kind of sets. So, this is what is known as comparison based algorithm, and we have seen these 4 algorithms: insertion sort, quick sort, merge sort and heap sort. They were all insertion based algorithms. We also have seen this following things, that for these 4 algorithms we have been using something around either log n or n space complexity, and the runtime has been around n square for the case of insertion sort and quick sort, and around n log n for the heap sort and merge sort. We also saw in the last class that when one asked the question that can one get an algorithm whose runtime better than n log n or space complexity is better than log n, then the answer is no. And in fact, we see that the space complexity has a lower bound of log n for comparison sort, and the time complexity for any comparison based sorting algorithms must be more than n over 2 log n over 2. So, these are all for comparison based algorithms, and the lower bound went through the decision tree model. So, here we are, we have seen 4 algorithms, and we have seen that there are algorithms with runtime O of n log n, whereas every comparison based algorithm has worst case runtime omega n log n. Or in other words, we are basically tight. We cannot hope to get better than something like heap sort in case of space complexity or time complexity. So, thus we have that in the case of sorting algorithms, we have an upper bound of order n log n, and space complexity has order log n. In the case of all comparison based sorting algorithms, so this one is clearly the comparison based sorting. It takes omega n log n, and So, we say that the time complexity for sorting is n log n and space complexity is theta log n. Now, when I say comparison sorting algorithms, I am not trying to restrict my algorithms into special case, because any algorithm that works for any setup must not be using the structure of this set. So, they must be comparing two elements and only then they can be doing something. So, in some sense this time complexity is n log n irrespective of whether it is a comparison based algorithm or not. But now comes the question that are there any not comparisons based algorithms, and in particular the answer is yes, but one has to use the structure of the set very carefully. So, thus the structure of the set becomes important, and one very important thing to note is that these non comparison based algorithms does not work for all inputs. So, let us start with, we will give two of the algorithms here. We will look at Radix sort and counting sort, both of them are non comparisons based algorithms. In the case of counting sort, we have assumed that the set of integers are coming from the set 1 to k, k is the parameter. So, this is kind of the structure of the set that we are looking for. So, we are now not saying that we have a set S of any set of integers, no, we have a set S of integers, all of them are between 1 to k, and the goal is remains same, to sort the elements of this set in an ascending order. Note that this kind of examples do come up a lot in practice, and therefore, this kind of algorithms can be very handy, but these algorithms will only work when the input satisfies this special condition. Let us set S be this set 2, 4, 2, 1, 5, 8, 5, 3, 7, 8, 1, 4 and 8. Here, although this set S has something like around 14 elements, we assume that every element of this set comes from this set 1 to 8, and now we need to sort it. So, to sort it, the first thing we do is that we will maintain count of how many times some element occurs. Thus, we have this table here where we have written 1 to 8, and then we go over this set S. Before we start this algorithm, we make all the counts to be 0, and then we go over this set one by one. We first go to number 2, and okay, the number 2, therefore, we update or increment the count in this second column by 1. Then we go to the next one, which is 4, and thus we increment the count. Then we again go to the next one, which is 2, and we increment the value in the second column by 1 more. So, it becomes 2, and similarly we keep on doing it till we have scanned through the whole set. After we have scanned through the whole set, we have this table below. We have how many elements of how many 1s is there in this set, how many 2s are there in this set, how many 3s are there in this set, and so on. Now, when we have to output this sorted list, see 1 is of course less than 2. So, I should write the 1s before. So, I first go to 1 and say that how many 1s are there, 2 1s are there, very good. So, I will write 2 1s here. Then it comes in how many 2s are there, okay, 2 2s are there. So, I will write them 2 2s. How many 3s are there, there is only 1 3. So, we will write 1 3 and so on, and we keep on doing this till we have completely put up all these elements. It was not a very hard algorithm, all we needed to do is count the number of elements or particular elements that are there. Note that crucially here we are assuming the fact that the set S is a subset of 1 to 8, or all the elements are coming from 1 to 8, and that is why we could do such an algorithm. Now, here is the pseudocode of the algorithm. pseudocode of the algorithm is again not hard. We maintain this array R, which has the count of each of the elements, and for as we move from 1 to k, we first set all the counts to be 0. If we find this Si element to be j, then I update the count on the jth element of R, and after we are done with this counting, which is at this state we are done with this counting, then we have this whole count, and then we go over this set R which has k elements, and as we go along, if I find the first element is S, we basically one by one write down the elements of 1 to k in S in such a way that the jth element is repeated R j times. So, this is the pseudocode of our algorithm. Now, what is the running time of this algorithm? All we did was that we did one pass through S, stored it in the array R, and then we did one more pass through R, and accordingly outputted the elements in S. So, all total we have required something like twice n plus k, or in other words it is ordered n plus k number of steps, and order n plus k is of course much smaller than n log n if k is small. Thus, if we have been given a set S of elements, all of which occurring from 1 to k, then we can use counting sort to correctly output a sorted list, and the time complexity will be order n plus k. This is not a comparison based algorithm. So, note that if k is small, something like a constant or even n, we can do much better than merge sort, heap sort, or any other sort. But the catch is that we do have to assume that this set of elements are from a restricted class. Here one thing to note is that what happens if I say give you a list of files. On each file there is a particular number. Okay. Its number is depending on the maybe the marks that this file has got, and I want to sort this whole files according to the marks. Now, one can say that the marks are only from 1 to 10. So, I have to now sort these marks from 1 to 10, all of which are from 1 to 10, and so I can use counting sort to sort them. But note that the way I have described the algorithm, you will be deleting the whole file. You will just keep a count of how many marks are there, of how many files have got marks 2, and then how many files have got marks 3, and how many files have got marks 8, or so on, and then accordingly you will just sort the marks. That does not help us at all, because we need to sort the files. Marks are just a parameter in the files. Please go and think about this particular algorithm and how one can quickly edit it or adapt it to handle this kind of problems also. Counting sort can also work with such kind of problems. The next thing to look at is what happens if k is large. So, let us take a small break now, and we will come back and talk about this problem. So, before the break we were looking at the counting sort algorithm, and we saw that if we have a set of elements, all of which are coming from 1 to k, then we can have a time complexity order n plus k sorting algorithm. It is not a comparison based sort. Now, what happens if k is very big? This algorithm does not help. For example, if k is n square, then it does not help at all, because this will give me order n square. But if k is small, this gives us a lot of advantage. So, the question is what if k is very large? So, at this Instead, we go to a new algorithm, what is called the Radix sort algorithm. Here we have a different assumption. We have a set of integers where each of these integers have k digits or less than or equal to k digits, and the goal is to output the sorted set of integers. Now, note that if something has a k digit, then the maximum size of this element in this set can be pretty huge. It is around 10 to the power k minus 1. So, this particular algorithm works amazingly good for even large integers, but only under the condition the integers have k digits. So, what is the idea of this Radix sort? It is simple. Say if I have given you a set of some integers, what will you do? The first thing to do is that look at the most influential bit or the what is called with the leftmost bit. I will sort according to the leftmost bit, because clearly if I have something like 100 and another one is 201 and another one is 301, I of course know that 100 will come earlier than 201, because 1 is less than 2, which is the first digit of those number. Similarly, 2 is less than 3, which is the first digit of this number. Once we sort based on the first digit, then we will sort on the second digit and so on. Let us see an example. So, here are a set which is a set of numbers, all of which have less than 3 digits. First thing is what we do is called bucketing of this digits based on the first digit. This Radix sort is also sometimes called the bucket sort because of this particular bucketing technique. What are the first digits? So, we will make this 10 buckets which are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we will go over this set S. So, we go to the first set which is 23 and say that okay, 23 has first digit 0. Note that first digit is 0 because we are looking at 3 digits. So, this 23 is actually 0 to 3. So, the first digit is 0. Whenever we look at bucket sort or Radix sort, we should always assume that the integers are exactly k digits. If they are not, we can put zeros in front to solve it. Now, we go to the next one which is 401, and of course, the first digit is 4, we put in the fourth bucket. The next one is 222 and we put them in the second bucket because the first digit is 2 and so on, and thus we complete this whole bucketing. So, we put all these elements in different buckets based on their first digit. Note that here the buckets are not sorted. For example, in this case of the zeros bucket, we have 22, 53, 88 and then 21 and then 47. But what is the fact is that all the elements in this zeros bucket is less than all the elements in the first bucket, is less than all the elements in the second bucket and so on. It is almost like quick sort to say. So, if we can somehow sort this first bucket and then sort the second bucket and then sort the third bucket and so on, then we will have a proper sorted list. The another important thing to do is that notice that this way, the way in which we have described the algorithm maintains the relative order of these bits. For example, 23 came first, so 23, then 53, then 88, then 21, then 47 and so on. So, the relative order of elements here remains when we do the bucketing. Now, once we have this bucketing done in the based of the first bucket, we have to do the bucketing based on the second bucket, and in the second bucket unfortunately I cannot draw them in this 2D setting, but imagine that I have a bucket of buckets. So, the zeros bucket is split into more buckets, and so I will be splitting it in terms of the second digit. First of all, 23 is a bucket, 53 is a bucket, 88 is a bucket, we go by one, then we find 21. Now, 21 must go to the second bucket, so I put it in the second bucket, and again we go to the 47 which should be in the fourth bucket, which should be before the fifth bucket, and this one and so on, until we have the bucketing done. Again note that after we have bucketing done, so in some sense the buckets are, you can think of, this is one bucket, this is one bucket, this is one bucket, this is one bucket, and this is one bucket. So the zeroth bucket here has been split into more smaller buckets based on the second digit, and even here inside the second bucket also the relative order has been maintained. For example, 23 was always before 21, and therefore they are still remain 23 before 21. Again it is still not sorted, so we need to sort it once again, and in other words I can look at the second bucket and just swap those two things, and thus we have the sorted list. So once we have that, we can just output the integers by reading the bucket, and thus will be done. So once two different integers are kept in two different buckets, then whatever I do with the first bucket does not matter, the integers will always remain less than the integers in the second bucket. So the relative order will never change. The relative order across first bucket and second bucket or even otherwise will not change. In terms of the time complexity, note that here for every digit we need to make a pass. So when we are looking at the first digit, we need to make a pass in the whole set and accordingly place it in the bucket. Once we are done with the first bucket, first digit, we go down to the second digit, and then we have to go bucket by bucket, or what it means is that we have to go and check every digit once. We have to look at the integers in the zeroth bucket once, then look at the integers in the first bucket once, and so on. So for every digit we have to make order n number of steps, and therefore the total number of steps that comes out is order n k, because k is the number of digit. For every digit we make n steps. In the case of space complexity, although the way I have described it, we have to make the buckets separately and so on, but it turns out that one can do this radix sort in place. That means we can reuse this set S. For example, here this same algorithm, let us see what one can do is that we can use this set just to partition this set into various buckets. Say at the first time we can say that there is no buckets, all the buckets are in the before 23, and after that when we are starting to sort it based on the first digit, what we do is we have no buckets here, then we will come to the 23 and we will put 23 in the second bucket, end of second bucket, and here we will have the end of fourth bucket. Then we come to this number 222. At this point I need to put this 222 in the second bucket, which is basically here. So I will swap this 222 and make a new bucket here, and so on. So thus, in other words, we can do this sorting in place. And now once we have sorted it in based on the first digit, we look at the second digit. Now again, when we look at the second digit, note that the relative order will be maintained, and since the relative order is maintained, so we have these buckets here that have come up. Even if when we sort it out, we will never be overlapping with each other, or we will never 151 will never go before any other object there, and therefore we can continue like this in the third digit, and at the end we will be getting our sorted list. So we will be doing this whole sorting in place. Crucial point of this radix sort is that this bucketing sort is not only in place, it is also a stable algorithm, because the relative order between two items always remains identically same. So as summary of the radix sort, if we have some set of integers, all of which are k digits, then the radix sort will correctly sort the set of integers. The time complexity will be order n log n. This is also not a comparison based algorithm. So here we are, the total understanding of the sorting algorithms. we had some comparison sort algorithms, which are the insertion sort, quick sort and merge sort, and we also saw that these are basically optimal. For example, heap sort runs in time order n log n, and we know that the worst case running time has to be omega n log n. But for special kind of inputs, there can be better algorithms. For example, we have seen counting sort and Radix sort. So, here are these two things, that if we have set of n integers, all of which coming from the set 1 to k, then the counting sort takes order n plus k steps. On the other hand, if I have a set of n integers, all of which have less than or equal to k digits, then the Radix sort takes only order n k steps. Here again, if k is very small, the first algorithm or the counting algorithm will do much better than the Radix sort algorithm. If k is less than log n, then Radix sort algorithm will do better than any algorithm which is comparison based. But if k is large, say something like order n square, then neither will the counting sort algorithm work, nor will the Radix sort algorithm. I mean, they will work, but they will not work in any better time than merge sort or heap sort. So, here are some questions that I would like you guys to go back and think about. So, if I give you n English words, can you design an order n algorithm to sort them in a dictionary order? It is a very natural question that comes up again and again in real life. Of course, one can come up with an order n log n algorithm, because merge sort and heap sort will sort it in order n log n. Can you get an order n algorithm? The other question is that it is something that you guys should go and think about. I had given you a lower bound argument in the last lecture, but where does it fail in the case of counting sort and Radix sort? It is true that counting sort and Radix sort are not comparison based algorithms, and they do not work for all inputs, but in this argument where does it fail exactly? So, we have come to the end of this lecture. To summarize, we have looked at some counting sort algorithms and a Radix sort algorithm. So, these are some non comparison based algorithms. With this, we come to an end of understanding sorting algorithms in general. In the next lecture, we will see more complicated algorithms, where this sorting algorithms will be used a lot as sub algorithms. Thank you.